Hello, welcome back to the class of natural gas engineering. Today's lecture is about the natural gas dehydration. And what does the dehydration means? That uh, what does the dehydration means that we have to remove the water vapors from the gas, natural gas. So the removal of the particulate water or water vapors from the produced gas stream, that's the water. Now, this is the very important step because this water vapor inside the gas, when it flows, it can cause lots of problems for us. Two of them are major problem. One of them is the hydrates formation, another one is the corrosion. And if the corrosion happen, and both of them has further consequences. For example, if corrosion happen, it can lead to the leakages, and if leakages happen, then consequence after consequence. And same for hydrates. If hydrates is happening, then it can malfunction many equipments. It can reduce the capacity. So many problems can happen because of this water one. So we have to rehydrate because we don't want the corrosion inside the pipelines or in the plant. So it causes the corrosion. It reduces the pipeline efficiency because of the hydrates formation. Well, it becomes a two-phase flow, then the flow accuracy will be compromised. It can cause the hydrate, as I say, and causes the plugging, total choke of the pipeline. And if I show you, like for example, if we have the pipeline like this one, and if there's a hydrates formation, if we have formation like this one, particulates, they will, hydrates can block it. So now, if you want the oil to flow, it cannot flow. It will be stopped here. It will be a problem. So we don't want this formation. And the other issue could be, this this one, this part sides could be, could comb the hydrates in on side. Now you see we have the reduced diameter of flow. So we have only this space to flow now inside. This small space to flow. This could be another issue because of hydrate. And if you have any flow meter device here, and if you have a two-phase flow, then the measurement will be compromised. Gas will not be accurately measured here. So what kind of methods we are using in order to dehydrate the water from this gas? We have many methods. Two of them are very common: membrane one and the glycol one. Well, what plants I have seen mostly based on the black glycol, diethylene glycol and triethylene glycol, and the membrane one. These are the most common types of dehydration methods that are used in industry worldwide. So it's an hygroscopic liquid. It means that the glycol has the ability to absorb water. So if we is a physical process, when glycol is passing through, it attracts the water and it will absorb the water inside. That's the glycol process going on. Then we have two kinds of glycol. We have diethylene glycol and we have triethylene glycol. So diethylene glycol has a low cost and very uh, good thermal composition. It has minus 474 boiling point range. 44% can be regenerated, and but the cost of operating is higher. Cost of higher operating cost, you know, higher capital cost means the cost of removing the water from the glycol itself, it costs you high. This is the issue with the diethylene glycol. In this one, it has the higher cost, okay, glycol, but the regeneration is 99.5%. Okay, 99.5% is the regeneration, and operating cost low. It means that it is easy to separate the water from the glycol. Okay, so we have triethylene glycol and diethylene glycol that are used on. Now I will show you a dehydration plant, and then we will further move ahead with this lecture. This is another glycol dehydration plant, you can see. So it has a main tower. This is its main tower. We call it the contactor. This is the main tower contactor, this one here. So now we will go further process and look about the project here. Now there are some parameters of this plant. Well, there are some fixed parameters here, as you see here, and then we have some variables from it. There are fixed parameters are those parameters that when you install the plant, you have to decide it. So after you finish the installation, you cannot then change them. There are some of them are like this. Then there are other kind of fixed parameter, for example, gas composition. The composition of the gas cannot be changed at particular time. Maybe after some time when the pressure declines, but gas composition usually stays the constant. Okay, and minimum and maximum gas capacity. How much plant, for example, you are designing the plant for 10 million cubic feet, standard cubic feet. So once you install 10 standard cubic, that's it done. Or maybe you want to. So once you fix the capacity of the plant, it is done based on the pressure and temperature. Okay, then the heat input, the fire surface area, the capacity of the column, and these capacity of the column, once you select them, that's it, you cannot change them. So after that, uh, that's why they are called fixed. And then we have the variable one. For example, how much gas is flowing inside the absorber. You can send it, let's say, 400 uh, you can send it 400 standard cubic feet per day, or 500 or 600 standard cubic feet, or 700 or 4000. So it depends like how much the gas can flow inside this absorber. Then how much is the water content you want to remove, how many percent. Some want 100% removal, some want 90%, 80%, like how much water needs to be removed inside. Then the glycol you are injecting, how much glycol circulation rate you are using, and how much is the concentration of the glycol. So these are the parameters that can change, and it also, the efficiency of the system dehydration plant depends on these four parameters also. First, when you want to design the dehydration plant, you must know what is the gas flow rate you are expecting from your wells, what is the gas temperature, what is its pressure, what are the customer's requirement and pipeline specs, where do you want to install it, what is your location, what is the availability of the equipped plants and other parts and equipments. So these all things matter, but especially the most important part is the pressure, temperature, and the flow rate, and the capacity, how much is you are expecting to clean it up. Now this chart shows this. If I show you, wait. This chart shows that how much water can be removed, how much water is carried by natural gas at various temperatures and pressures at certain point. For example, the below one here you can see is the temperature, and these lines are for pressure. So for example, at 80 degrees centigrade, okay, and if you go ahead here at the pressure line of this one, it can keep almost 7 pounds per million cubic feet here. But if the temperature is reduced to, let's say, 1000 psi, 1000 psi here, then you can see the water is around 35 uh, pounds per million cubic feet. So as the pressure is declining, okay, as the temperature, and if you increase the temperature to 90, same pressure. So as the temperature is increasing, the capacity of water per is, removal is also increasing at the same time. So here we have the same pressure of 1000 psi, but the temperature of the gas is 70, 90, and 110. As you see that if the temperature is 110, the capacity of the gas to carry water is around 90 pounds. if we have the 90 degree centigrade, then it can carry around 50-40 pounds. The temperature is 70, it can carry around 25 to 30 pounds. So temperature plays an important role in the water content of removal. Now this is about the pressures. So this one, we are keeping the pressures temperature same at 100 degree, but we are changing the pressure. For example, here is 2000 psi, then is 1000 psi, and then is the 300. As you see that as the pressure is declining, the water removal is also 18 points. This is 180, this is 60. Water removal, water content can be taken out from this temperature and pressure. So by playing with the pressure and temperature, you can remove the water uh, from this natural gas and so on. Now we talk about this natural gas dehydration plant. Well, the major equipment here is this contactor tower. So this one is the major equipment here, this one. Then the other major part it has is this one, where the glycol is regenerated. So here actually the glycol and the gas meets, and the water is filled with the glycols, and then glycol comes out with it. The dry gas is going out of here in this case, and this the rich glycol is going from this high pressure filter through this process inside this reboiler, where we give it a very high temperature. Based on the high temperature, the glycol and water are separated, and after we have the clean glycol, the glycol then goes back inside this one, this blue one, inside this one, and goes back to the contactor. So it's a recycling system, circulation system, and it goes on like this. So it has major two parts. One is the contactor, another is the reboiler like this one, but here is horizontal because we are dealing with water, so we have the horizontal one. And then we have the two small scrubbers, and their job is to remove any free water contaminants uh, from this gas, acid gas that we are removing. So here is the tower. Here is the very detailed picture of it. You can see here this gas is coming out of here. Then it has the baffling plates inside, cartridge type of plates. And here inside this one, the gas, okay, the gas is going up. After removing those baffling plates, gas from here it goes out, dry gas out. From here the dry gas goes out. This is the system. And the rich glycol then travels from here, from this line. From this line travels inside this tower. And here we have the reboiler. We boil it, and water vapors are removed from here. Okay, and this is the storage tank where this glycol is stored, and after the storage the glycol is sent back to the system. So now I will show you the video which shows the similar process here. So that was the basic process, and now I will show you the further of this one. is also
Call passage into the tray below to prevent gas from bypassing the bubble caps. As the glycol spills downward through each succeeding tray, it becomes wetter with the water it has absorbed from the gas and collects in the bottom of the contactor saturated with water. This wet glycol then flows out of the contactor and through a filter where any solid and abrasive particles or tarry hydrocarbons are removed before it enters a pump. From the pump, the cool, wet glycol is sent to the surge tank. The surge tank is a holding tank which stores hot, dry glycol produced by the reboiler before it's sent to the contactor column. However, the cool, wet glycol does not actually enter the surge tank. Instead, it flows through the surge tank in coils. This allows for the heat exchange process to occur, which we mentioned in the first section. As the cool, wet glycol flows through the coils of the surge tank, it's warmed slightly before it enters the gas condensate glycol separator. Conversely, the hot, dry glycol stored in the surge tank is cooled before it enters the contactor column. After leaving the coils in the surge tank, the wet glycol enters the gas condensate glycol separator. Now, the purpose of this vessel is to remove the gas and condensate hydrocarbons that were accumulated by the glycol on its path through the contactor. Heat will cause the hydrocarbons to separate from the wet glycol solution. Now, this hydrocarbon condensate is skimmed off the glycol and disposed of, and any remaining gas vapors will exit at the top. From the gas condensate glycol separator, the wet glycol then flows in a tube through the reboiler where it's heated slightly before it enters the still column. Inside the reboiler still column is a section packed with ceramic or stainless steel saddles. The glycol spreads uniformly over these saddles and drips down through the packed section. The distillation or cooking process is started in this section to boil the water out as a vapor from the glycol. From this packed column, the wet glycol drops into the bottom of the reboiler. Here, a source of heat is circulated through a tube in the lower section of the reboiler to heat the glycol solution up to around 370 to 400 degrees Fahrenheit, which is just below the boiling and decomposition point of triethylene glycol. Usually, waste heat from compressor or generator exhaust gases can be used as a heat source, but many installations also use a gas-fired heater. Remember, the temperature of the glycol in the reboiler is critical and is controlled at this point. Any higher and the glycol will begin to decompose, requiring costly replacement. As the glycol begins to heat, the water trapped by it begins to boil and moves upward through the still column as steam. Mixed with the steam will also be some hot glycol vapors. As this mixture passes upward through the still column, it comes in contact with a cooler part of the column, and the glycol vapors will condense and drop back into the reboiler.
So this was the process of dehydration that we are talking about. So in this plant, if I show you the diagram, actually here is this is the first step. This is called the inlet scrubber. An inlet scrubber, it has any free water or any contaminants, they are removed here. Okay. Then this gas, wet gas, the gas which has water is called the wet gas. It goes here. Here. Then this gas flows up. Okay. Then on the other side, we inject the dry glycol from this side. This yellow one, as you can see there. Dry glycol is injected here. This dry glycol is going down. Here they meet each other. Okay. And the clean gas then goes out like this one. It goes out like this one. Okay. And the dry glycol, when it goes down, as you see here, this from the yellow it becomes blue. Okay. So it becomes a wet glycol. The glycol which has water. Now this wet glycol then comes out of here. This is the high pressure filter. Any contaminants are removed. Then this one, it goes here, this blue line. Then here we have the heat exchanger, reboiler. It boils it. When it is boiled, the dry glycol then goes inside here. The dry glycol which is free from the water. Okay, and the water then is sent through this tank, three-phase condensate. The water is sent here. All the water is sent here, and is water vapors. We remove them or we dump them or whatever we do. Then the lean glycol, which has which is clean, then again from here send back through this pipe back to back channel. So that's the overall process of this amine process. Now the first step is inlet scrubber, and we said that if the inlet scrubber here, this part, it removes it if it has any free liquids, eliminates any free liquid from the gas tank. Requires liquid level controller. So if any mist or any free liquids or any contaminants are here, they are removed in the scrubber. Okay, nowadays we have modern tower absorber which has lower part is scrubber. I mean it has a built-in scrubber which removes any free water also. It has a lower cost than operating this scrubber separately because they are together, so they take less energy to manage it. Now another one, here is the process. Absorber, pump, heat exchanger, because this rich glycol goes here. Okay, reboiler, wet gas goes in, the wet gas goes out, wet glycol flows here, and this dry, after the reboiler boils it, the water is removed from the glycol goes back here in the absorber tower. Like that. This is the process. So, well, this is the main absorber tower where glycol and water, glycol and the wet gas, they meet each other and they sort it out. The temperature here is kept around 60 to 135 degree. Pressure, quite flexible with the pressure, 100 to 200, 600, 2600 psi, and lower temperature that gas will cause the foaming. Be careful for the temperature because there could be glycol losses or foaming issues inside this tower. So we make sure that we monitor the temperature and the pressure inside. Glycol circulation rate, and so on. The glycol concentration pH value should be 7 to 7.5, and mist extractor should be used. Okay, so this should be the one. Here is the old tower. So holding tank for a dry or lean glycol before it goes to the glycol pump. This is the surge tank. So surge tank is actually, it holds the glycol because it's a complete cycle. So the lean glycol is kept here, and from here it goes back through here, through here. So we need a storage tank. So it works as a storage tank like the water tank at your homes in order to store the glycol so that we can send this glycol to the system after the campaign. Then we have the reboiler. Purpose is to remove the water, boil the glycol, wet glycol, and remove this water from this glycol. The temperature ranges from 375 to 400 degree, and fire tube heat flux 6,000 to 8,000 BTU, and fire tube must be free of deposits, salt, coke, stripping topper, still column where wet or rich glycol is injected for water removal. Okay, packed with ceramic settles. This is still column. Then finally, we have the last one where we use this still column to remove this water vapor from the remaining glycol, and we use it under the 225 degree Fahrenheit in order to use this one. Then we have the glycol pump, and should be correctly sized. It's a high pressure charcoal filter in order to uh, give it a pressure enough so that we can, all the process goes on in this term. Then we have the three-phase separator. It separates any liquids that might get trapped over with the glycol, such as, so when the glycol comes in, it removes the liquid out of it, and if it has any other hydrocarbon, so it has actually a three-phase, so it's any solids, contaminants, water, uh, hydrocarbons, they are removed in this three-phase glycol separator. So that's all about this gas dehydration, and where glycols are used to remove the water. This was the plant and the basic equipments used in this dehydration process. So see you in the next lecture where we'll talk about this nitrogen rejection unit. Thank you very much.